this theorem can be used to show some interesting phenomena that relate to phase colorings. For example, we can show that being two-phase colorable is equivalent to being Eulerian. So let's look at the proof. So being Eulerian is equivalent to the dual graph being bipartite. This was an exercise from the problem session. The dual graph being bipartite, well, we have already talked about being bipartite being equivalent to being two colorable. So the dual graph is going to be two colorable with respect to the vertices, because we can color the vertices in two colors. But by the previous theorem, the dual being vertex colorable means that the dual of the dual is two colorable with respect to the faces. But the dual of the dual is the graph itself. We're dealing with plane graphs, so the dual is well defined, and we get that G itself is two colorable with respect to the vertices. Notice that the condition for Eulerian, namely where the graph has to be connected, is immediate because all maps are connected by definition. So this brings us to a notion of four-colorability. Why is four-colorability interesting? Because we have the four-color theorem for planar graphs, which is the statement that every simple planar graph is four-vertex colorable. This was one of the major theorems of the 20th century. And on the other hand, you can formulate a similar theorem for phase colorings. So the so-called four-color theorem for maps, which is the statement that every map is four-colorable with respect to the faces. And in fact, these two are equivalent. So the four-color theorem for planar graphs with respect to vertices is equivalent to the four-color theorem for maps with respect to faces. Well, if you have a map, then the dual is a simple plane graph. Why is it simple? Again, for the same reason, the lack of cut sets of size 1 or 2 means that we have no cycles of size 1 or 2. So in the previous theorem, if you can color the faces in a certain way in G, this will correspond to a vertex coloring in G star. So, and conversely, if you start with a simple plane graph, as we saw before, the dual was a map. So again, if you can color the original graph in a certain way, you can color the dual in the same way with respect to the faces. So this means that if you want to prove the four-color theorem for planar graphs, you can just as well prove the four-color theorem for maps, which is already nice. And that's why we can call these theorems just the four-color theorem, because the two are equivalent. So one fine thing about this is that now when we deal with maps, we can simplify the proof of the four-color theorem, or the necessary proof. So to prove the four-color theorem, meaning that to prove that every map is four-face colorable, it's enough to prove that for cubic maps. So what does this mean? Well, cubic means that each vertex has degree 3. And remember, in a map, each vertex has degree at least 3. We excluded degree 1 vertices because they would be at the end of a bridge, and degree 2 vertices because they would have a cut set of size 2 around them. So we really only have to deal with vertices of degree more than 3. So what this theorem says is that if you can color any map that is cubic, so if you can four-color the faces of any map where each vertex has degree 3, then you can do that for any map. So how to prove such a thing? Well, as I just explained, in a map, all vertices have degree at least 3. So if you have a face or a vertex of degree more than 3, replace it with a patch. So how does this work? This is the easiest to show with a drawing. So if I have such a vertex V, and I have my faces F1, F2, F3, F4, and F5. So in this example, there are 5 faces. Then what I do, I replace it with a patch. So I have my faces now, let's call them F1, F2, F3, F4, and F5. But now I do this. It's kind of an ingenious way. There we go. I get yet another face, F0. Why is this reasonable? Why is this help? Well, with this replacement in my new map, instead of this degree greater than 3 vertex, I now have a bunch of vertices of degree 3. Also, the faces F1, F2, and so on are adjacent, share an edge, if and only if the corresponding blue faces share an edge. Again, sharing a vertex doesn't matter. So F1 is not forbidden from having the same color as F3, and neither here. So I have replaced my map here, well, around this vertex, with a new map with only degree 3 vertices. This means that if I can color this new map in 4 colors, then by using the same colors for F1 through F5, I will be able to color my original map. Because the edge sharings between the faces are the same. And this face F0, well, I just forget about it because it's certainly it's not in the original map. So doing this for every vertex of degree 3, you get a cubic map, and if that map is 4 colorable, then so is the original map for the reasons that I mentioned with edge sharing between the red faces and the blue faces. Okay, so this theorem tells me that instead of dealing with random maps, if I want to prove the 4-color theorem, it's enough to deal with cubic maps, maps where all vertices have degree exactly 3. So why is this nice? It's because cubic maps are generally easier to deal with. For example, as an exercise, you can prove that a cubic map is 3-face colorable if and only if each face is bounded by an even number of edges. So we have an easier grasp of the notion of k-face colorability for such maps. So, of course, still the proof of the 4-color theorem is very difficult, and if you stay tuned, I'll give the general idea of the proof. But as I said, the proof was performed using computers and was one of the major achievements of the late 20th century.